Okay, let's do some heat conduction and blackbody example problems. Our first problem. A cylindrical iron bar has a diameter of 2 centimeters and a length of 1 meter. The sides are insulated so that heat can only flow in and out of the ends. One end is connected to a heater which injects a constant power of 20 watts into the bar. The other end is submerged in ice water, keeping it at 0 degrees C. When the bar reaches steady state, what will the temperature of the side connected to the heater be? Okay, so we're given, we know that it's iron, so we can look up in our book and find the thermal conductivity of iron, so we know that. We know the length of the bar, we know the diameter of the bar, and we know the power flowing through the bar, right? Because if we're in steady state, if we inject 20 watts in, 20 watts has to flow down the bar and 20 watts has to flow out. So this is what we know: the thermal conductivity, the length, the diameter, and the power flowing through the bar. Alright, our basic equation for conductivity is that power is thermal conductivity times area divided by length times the difference in temperature of the two ends. So temperature of the hot side minus the temperature of the cold side. Alright, and alright, this problem shouldn't be too hard. We know this, we know this. The area, what's the area that we plug into there? The area is just pi r squared, which is pi the diameter over 2 squared. Alright, so if we plug that in for area, we know temperature cold, right, at 0 degrees C. Now we just have to solve this equation for T hot, right? So let's go to our next page here. So power is equal to K, and our area was pi d over 2 squared, pi area over L, T hot minus T cold. Alright, so we'll just multiply stuff over here, so we get power times the length over K pi d over 2 squared. That's equal to T hot minus T cold. Alright, we know T cold, we just want to find T hot. Right, that's how hot this will get. Alright, so that's just going to be power L over K pi d over 2 squared plus T cold. Alright, first of all, units check. That has units of temperature. Alright, I'm not going to do it, but I recommend you go through and check, did I get the right units? If my units are wrong, I made a mistake. Alright, let's think about how this thing scales. First of all, if I increase the cold end of the bar and I have the same power running through it, the temperature should increase linearly everywhere, right? And I see that. If I add 2 degrees here, I get an additional 2 degrees here. So that makes sense. If I increase the power, the temperature ought to go up. If the rod is longer, right, then the heat, there's less conduction, right? It's harder for the heat to flow, so it takes a greater temperature difference, which would mean that the end would get hotter, right? A heater gets hotter if it's harder for that heat to flow away. If the thermal conductivity is lower, it should get hotter. If the diameter is smaller, it should get hotter. So it seems to scale the way that it should. So I'm going to assume that I did it correctly, and I'll let you check the units and plug in numbers. Alright, here's our next problem. This is a more complicated problem, kind of like what I expect the students in the physics major section to be able to do. So if you're not in the physics major section, this may seem a little difficult, but that's okay. A diver is submerged in a diving bell. The bell is essentially an iron sphere 6 meters in diameter with a spherical cavity in the center, which is 3 meters in diameter. So my diving bell is a big sphere hollowed out with a sphere in the middle, and that's 3 meters, and this diameter is 3 meters, and this diameter is 6 meters. Alright? And of course we know the radius, because the radius is just half the diameter. There's a heater inside the diving bell to keep the diver warm. The surrounding ocean is at a temperature of 5 degrees C. If I want to keep the inside of the diving bell at 25 degrees C, what power must the heater put out? Now, so we know the temperature of the outside, we'll call that T cold, and we want the temperature on the inside to be some temperature T hot. Alright? Presumably I can look up the thermal conductivity of iron that the bell is made of, right? I forgot what I was going to say. Oh, so the power, and then I've got a heater in there that's generating the power. So I want to find what I want the power to be flowing out of here, such that I have the correct temperature in the middle. And now, of course, the diver is also going to emit power as he, metabolizes carbohydrates in his body. But we'll neglect that. We'll just assume all the power is coming from the heater. All right, so the basic equation that we have is power is equal to thermal conductivity, cross-sectional area over L, times the temperature difference, T hot minus T cold. Unfortunately, our rod is not a rod, it's a spherical shell. All right, it doesn't have a fixed area. So what I'm going to do is I'm going to take this problem, and instead of solving the whole thing at once, I'm going to break it up into a bunch of little spherical shells. All right? And I'm going to look at the power flowing through one little shell. Okay? Now, if I look at this, if I unfold it, if I could unwrap this thing and stomp on it, I would find, right, that the surface area on this side of my conductor is smaller than the surface area on the outside. But in the limit, as I have an infinite number of infinitely thin shells, each shell has the same surface area. If I have a little infinitely thin shell here, in the limit as that shell is infinitely thin, the surface area on this side of the sphere and the surface area on that side of the sphere are the same. So what I'm going to do is I'm going to write this equation, but just for one of my little infinitely thin spheres. So the power flowing through that sphere will not be infinitesimal, right? All of the power flowing out of my diving bell will go through this infinitely thin shell. It's not infinitesimal, all right? So the power is equal to K. What's the surface area? It's just going to be the surface area is 4 pi radius squared, okay? What is L? L is that distance right there. It's the distance that the heat is going through. And that's infinitesimal. We'll call that dx, all right? I'll just call that dx, all right? No, dr, because I called the radius of this r. dr is a little change in r, so it's dr. Okay, and then I have to multiply by the temperature difference on this side versus this side. Well, it's an infinitesimal shell, so the temperature difference is going to be infinitesimal too, so I'll call it dt, all right? And if the power is flowing in this direction, all right, the temperature is going to be hotter on this side and colder on this side, and so dt will be positive as r increases, so I don't need to add another minus sign, it looks like, out front. So there's my equation. Let's write that nicer. The power flowing through the shell is K 4 pi r squared times dt over dr. And that's just a derivative, all right? So what I want to do, I want to solve, this is a differential equation. The way I'm going to solve it is I'm going to get all the stuff with r on this side and everything with t on this side, and then I'll integrate both sides, all right? So I'm going to multiply everything with r over to this side. So it's going to be power times dr, so I multiply both sides by dr, and let's divide both sides by r squared, and that'll get that over there. And then what I'm left with on the other side is 4 pi k dt, all right? Did I account for everything? Yes. So now what I can do is I can integrate both sides, right? I can get rid of the dr and the dt by integrating. The dr side, where am I going to integrate from? I'm going to integrate from the inner radius to the outer radius, right? The inner radius is, so the inner diameter was 3 meters, so I'm going to integrate from 1.5 meters. The outer diameter is 6 meters, so the outer radius is 3 meters. So I'm going to integrate from 1.5 meters to 3 meters, and this is what I'm going to integrate. On the other side, I'm going to integrate from the temperature on the inside, right? So if I'm integrating this side from inside to out, I have to integrate the other side from inside to out, because I have to do the same thing to both sides of my equation, right? So this will start at the inside, we have temperature hot, and outside we have temperature cold, the temperature of the ocean, the temperature we want our diver to be, all right? On this side, all right, let's write this on another page. So what we have then is I have the integral from r inner to r outer of p over r squared dr, and that's equal to the integral from the temperature on the inside to the temperature on the outside of 4 pi k dt. All right? So this side is really easy, right? Because the 4 pi k, those are all constants, they come out. And the integral of dt is just t evaluated between the limits, and I just get t cold minus t hot. All right? So that's this integral right here. This integral over here, what's that going to be equal to? Well, the power is a constant, so it comes out. I just have power integral from r inner to r outer. And 1 over r squared, I like to write it when I'm doing integrals like this, r to the negative 2 power. It's the same thing, right? But that is easier for me to think of, because then I go, oh, it's just the integral of some power of r. And the way I integrate is I raise the power, right? So that's going to be r to the -1 times -1. And I check that by saying, what if I take the derivative? If I take the derivative, I multiply by a -1 and then lower the power. Okay, I do the derivative of that and I get my integrand, so I must have done the integral correctly, right? And then I evaluate that from r equals r inner to r outer. All right, so that's going to be equal to power times -1 times 1 over r outer minus 1 over r inner. Did I do that right? Okay, so then when we solve this, okay, I'm going to set this equal to that. So 4 pi k T cold minus T hot is equal to the power times, I've got this minus sign, so let's just flip these two, 1 over r inner minus 1 over r outer. All right, and so now I just have to, these are all things that I know, I just have to solve for power, so I'm going to leave that step to you. But first let's take a look at it, all right, and see if this all makes sense. First of all, T cold is going to be less than T hot, so this side is going to be negative. We wanted our power to be positive. If I look at this, r inner is smaller than r outer, so 1 over r inner is going to be bigger. So it looks like I made a mistake. It looks like I really needed a minus sign up here. So as r goes out, dt, oh, I didn't think of this. As I go out from hotter to colder, dt is negative. I did need a negative sign. I thought that through incorrectly, right? As for a positive dr, dt will be negative because I'm going from hot to cold because the inside is hotter than it's higher temperature than the outside. So I should have put a minus sign in there. If I carry that minus sign all the way through, then I would have, put a minus sign somewhere, whatever. I would have gotten something that made sense. So that was a mistake, but it was an easy mistake to catch and fix, all right? Okay, look at other things. If the inside temperature is higher, okay, let's get rid of that minus sign. Let's put it right here. This makes more sense, all right? This is more useful. If my outside temperature, if I want my inside temperature to be higher, that makes this bigger, I have to put out more power. That makes sense. If the outside temperature gets bigger, I subtract that. That means less power. That makes sense as well. More thermal conductivity. Iron is very thermally conductive. That makes for more power. If I have a bigger outer diameter, all right, bigger outer diameter makes this smaller. I subtract off less, right? Which means, so if I have a larger outer diameter, then if I have a larger outer diameter, I subtract less, right? A larger outer diameter means basically it's like more insulation, right? Bigger inner diameter acts like less insulation. All right, so I can go through this and see that if it scales the way that it should. And then once it does, once I'm happy that the units work and everything scales the way that it does, I plug in my numbers and I get my answer. Okay, here's our last problem. A filament made of 0.02 millimeter diameter wire, which is 2 centimeter long, has an emissivity of 0.5. A current runs through it, resistively heating it with a power of 100 watts. Assuming that the temperature of the filament is high enough that blackbody radiation is so much larger than heat loss due to convection or conduction, and absorption of radiation from the environment is negligible. That's not very well worded, but what I meant to say is we don't have to worry about convection or conduction or absorbing anything from any radiation from the environment. What will the steady state temperature of the filament be? So our basic equation then is, we know that for an object at some temperature, it will emit blackbody radiation, which is the Stefan-Boltzmann constant times the area, surface area of the object, times the emissivity, times temperature to the 4th power. All right, so what we're saying is, I've got this filament. It can also conduct heat through the wire hooked up to the filament, right? But it can also convection. Maybe there's air around my filament. Also, the room, my filament is in a room, right? And the walls of the room are emitting blackbody radiation, and it ought to be absorbing that. But the point is, if our filament is really hot, the blackbody radiation goes up as temperature to the 4th. So if this temperature is high enough, presumably those other processes are negligible, and I can just worry about this, all right? So I know the power coming into my filament, that's given, so I just have to solve for the temperature, all right, of the filament. So I just solve for temperature, and I'm going to get the 4th root of power over the Stefan-Boltzmann constant times area times the emissivity. All right? And once again, standard, look up the units for all of your things, put it together, make sure you get units of temperature in the end. Does it scale the way we expect? If I put in more power, the temperature goes up. If I have more cross-section, right, if I squished my wire so, you know, it had the same resistive heating but had more surface area, it's going to emit faster, so the temperature will be lower. That makes sense. If the emissivity of my wire is smaller, all right, or if this gets smaller, it doesn't emit as well, the heat doesn't come out as fast, and I'm going to end up at a higher temperature. So it seems to like follow what we would expect it to do. All right. In the limit, as I put no power in, it takes no temperature to get there. All right. We've neglected a lot of other stuff at that point, though. So it looks like my answer is reasonable. I'll let you put the numbers in and check the units.